Alright, so our question states that we have two loudspeakers that emit 400 hertz notes. And it says one speaker sits on the ground and the other speaker is in the back of a pickup truck. You hear 8 beats per second as the truck drives away from you, and it's asking what's the truck's speed. But in this case, it's just best to remember that we're trying to find the velocity of the truck. And I was kind of confused at this at first, but as I did some research, I figured out that this question is an example of the Doppler effect. And this is the equation that comes from that effect right there, and there's only one equation, but we can manipulate this equation to be able to find the velocities of our observer as well as the velocity of our source. And in this case, we're finding the velocity of our source, and one thing that we know is that our observer's velocity is 0 since it is stationary. So this gets cancelled out right here, or is just 0, so there's nothing there, leaving us with the frequency of the observer, that what they hear is equal to the velocity of sound divided by the velocity of sound plus the velocity of the source, which is the truck in our case, multiplied by the actual frequency, which is 400 hertz. So this is what we have right here, which is the equation, but I just wanted to point something out, that depending on whether the source is traveling in the observer's direction versus the source traveling away from the observer, you use two different signs. So if it's traveling in your direction and the observer is stationary, we use this negative sign right here, and if it's traveling away, we use this positive sign right here. And I just used this drift because I thought it was pretty cool. This just shows you that as a source goes towards the observer, you can kind of see that the waves get compressed as it goes towards it, but as it's driving away from the observer, the waves kind of stay the same. And a good example to kind of like visualize in a real example of the Doppler effect is when you hear a kind of an ambulance sound, where as it's coming far away, it's very high pitched, but as it comes really closer, it gets like lower pitched as it's like really close to you, and as it drives away, it gets higher pitched again. So that just shows you like how the sound waves interact with the observer and what the observer picks up. So now we just plug in the numbers into our function, and I'll show you how to get certain variables, because certain variables we don't have straightforward. So to find the observer's frequency of sound, we don't have that, but we do know that the 8 beats per second in the question tells us the frequency difference, which is the difference between the observer and the truck sound. And what I'm going out here is that we know that the difference in the frequency is equal to the actual frequency subtracted by the frequency of the observer. And then we can manipulate the variables to be able to get the frequency of the observer equals the actual frequency subtracted by the difference in frequency. And then I just plug in the numbers right here, our actual frequency being 400 hertz and the difference in frequency being 8. And that just leaves us with 392 as our f of O. Our actual frequency is given to us from the question, and the velocity of sound isn't given to us straightforward, but we can Google search it, and when you Google search the speed of sound, you get 343 meters per second. And then as for the velocity of the source, that's what we're trying to find, and now we just plug everything into the equation. We have our f of O equals our f of S, in parentheses the velocity speed of sound, and the speed of sound right here, and then the velocity of the source. So since we're trying to find this, we just want to isolate this variable. So when you isolate it, you get this whole thing right here, and when you plug everything into the calculator, you do get 7 meters per second, which is kind of great because it's a full number. And that's our answer.